Yeah. So before I go for actual examples on this t distribution, what I will do is I'll write down the remarks. The first one, when n is less than 30, we use t distribution. This is also called student's t distribution. Just remember that. Second one, if t with n minus 1, look, this suffix is called the t with n minus 1 degrees of freedom, which is called the calculated value. Calculated value. This is less than t with n minus 1 alpha. This is stable value. What is alpha? Anyone? Alpha is the level of significance. Okay, so look, whenever you are doing these calculations, you need to have some certain freedom. I mean, if I say mean is say 30, and if it is nearby 30, say 30.56 or 30.32 or 29.96, it is nearly equal to 30, and some region is always accepted, right? So this alpha takes care of it. uh, I wanted to show you actually, say, if I have this for an example, the tabular value, I said that it may be given in the question, but if it is not, so let me show you that. So in case if you don't have the tabular value given to you in the any of the statistics books, what happens is that there are these statistical tables available. Okay, and for the statistical table, there all the distributions are there. Okay, so I'll just share my screen. Say t. So you can simply Google the table, t distribution tables. So you can see here. So see. So F distribution with degrees of freedom. So this left hand side represents the degrees of freedom. So this 1, 2, 3, 4, 5, 6. Look, the till 30 it is given. So degrees of freedom up to 30 are given in this table, and this top column, this represents this level of significance. Okay, generally what we need is 1% and 5%. In most of the cases, level of significance is 1% and 5%. So if I say 5%, then it is 0.05. So I have to look at, so if I want this t distribution with degrees of freedom 6 and level of significance 0.05. So 6 and 0.05, this is 1.943180. Okay, but remember that when we are talking about say the hypothesis the null hypothesis, in this case we have to third remark is that the population is distributed normally. Okay, we should always make sure that if I am applying students t distribution, then population should be normally distributed. Okay, should be normally distributed. Normally distributed. Okay, so now normal distribution, we have seen this. We have a bell-shaped curve in the normal distribution. This y-axis. Now, when I'm defining this alternative hypothesis, we talked about one tail and two tail. Okay, say h1 I can write as h1 as mu less than mu naught, or mu greater than mu naught. Okay, if both the cases are available, if this is and, okay, so if there is and, then my critical region will be on both the sides, right, this as well as this. But if I'm just taking my alternative hypothesis as this one, mu less than mu naught, or I'm taking this h1 as mu greater than mu naught, then we have to use the one tail and two tail. So that's why here you can see that it is written that right tail only greater than values are here. So I can also choose, say for an example, two tail. So there must be tail. So if you take two tail, so this table has both the values, two tail and one tail. So if two tail is there, then 0.05, 6, and I will go for this value 2.447. In one tail, what will happen is one tail 0.05 is here, 6 is here, so that is 1.943. So this is how we differentiate. Okay. Similarly, we can search for say chi-square. Chi-square table. So again, you can see that the degrees of freedom, what was the formula? K minus P minus 1, right? So we have the degrees of freedom. We have this level of significance. 0.05 is there, 0.01. Only these two columns we need. I said that in maximum cases we are going to have this. So you just look at the degree of freedom, level of significance, and you will get the tabulated value. Okay, fine. So let's get back to our discussion. Yeah, so I had to complete this statement. If calculated value is lesser, then hypothesis H naught is accepted. Bracket shouldn't be there. Fine. That's all about the theory part. Let's go for some examples here now. In order to start new ST bus to a certain remote village, it is required to get the average fare of rupees 400. It is required to get average fare of rupees 400 daily. Reports on number of passengers for 21 days. For 21 days revealed that the average daily collection of fare from passengers for 21 days no, passengers was rupees 390 was rupees 390 with standard deviation rupees 40. Do these data support the demand? For starting new bus to the village. So what is happening here? So if we want to start a new bus, so average fare has to be around 400 daily, and if it happens to be 400 daily, then this data will support the demand, right? So my null hypothesis here H naught is going to be that mu is equal to 400. Mu is equal to mu naught is equal to 400. right? And the alternative hypothesis. What should be the alternative hypothesis? That mu is less than 400. Look, if it is greater than 400, it is still accepted. Remember that. If it is greater than 400, still it is accepted. So this is one tail which is going to be required. One tail, which end is required? The left hand side one. Okay. So alternative hypothesis is this. By our t distribution formula, what is our t distribution formula? T distribution with n minus 1 degrees of freedom is
Is
what was the formula? X bar minus mu naught divided by s upon under root n. Okay, what is x bar? X bar is the mean of the total population. Look, remember that there are two things here. X bar and mu naught both are average, but there is a major difference. The major difference is of the total population, whatever is the mean, that is x bar, and whatever random sample I am defining, right? So in that case we will have this. So reports on number of passengers for 21 days. 21 is going to be the samples size n. Okay, revealed that the average daily collection of fare from the passengers was rupees 390. So x bar is 390. What my mean is, the hypothesis whichever is, that is mu naught. What is s? S, we wrote down the formula where s square is equal to summation xi minus x bar square divided by n minus 1. So if I multiply and divide by n, what I'm going to get is n into variance of sample divided by n minus 1. Okay. So let's put the values. Standard deviation is given to be 40. What will be the variance? What will be the variance? If standard deviation is 40, then the variance is square of the standard deviation. So variance of the sample is 40 square. What is the sample size? 21 days, right? So let me just write down all the details. N is equal to 21. X bar, mean of the sample. What is the mean of the sample? 390. Variance of sample. The variance of sample is 40 square, which is 1600. So the value of S is going to be 21 into 1600 divided by n minus 1, which is 20. So the value is 40.98. Let's put all the values in this. Remember that I have to take the root also here. S is equal to under root of this, as S square value is this. Fine. So T with how many degrees of freedom? 21 minus 1, which is 20. X bar, which is 390, minus mu naught 400, divided by S, the value of S is 40.98, divided by under root n, which means under root 21. So this is minus 10 under root 21 divided by 40.98, and the value is minus 1.1180. What is this? This is calculated value. So as shown earlier, we will look at the tabulated value T with 20 degrees of freedom, level of significance 5%, 0.05. So that is 1.725. This is table value. So whether your hypothesis is rejected or accepted, H naught is rejected if T20, the calculated one is less than minus of T20 with level of significance 0.05. This is stable one. So minus of, note that in the table there are positive ones. So that is minus 1.725, right? This value. This is minus 1.1180. So what is happening? Minus 1.11 is greater than minus 1.725, right? So if greater, then what we do? H naught is accepted. The data supports the demand of people. Data supports the demand. Why we are accepting even if the calculated value is greater? Anyone can give the logic or not? We are doing the calculations on the negative side. Remember that when I was explaining, I was talking about the right hand side of the bell shaped curve. If it is on this side, the left hand side, this is the region, the calculated value is larger than the tabulated value. So tabulated value is here and this is your calculated value. So it turns out to be in this region, right? Which the acceptable region. This is the acceptable region. So being larger on the negative side is going to be accepted, right? And that's why we have accepted this hypothesis. Next example. Suppose that sweets are sold in packages of fixed weight in packages of fixed weight of contents. The producer of the package is the producer of the packages is interested in testing that is interested in testing that average weight of the contents in package, average weight of contents in package is 1 kg. Hence a random sample, hence a random sample of 12 packages is drawn and their contents found and their contents found in kgs is as follows. 1.05, 1.01, 1.04, 0.98, 1.01, 0.97, 0.99, 0.98, 0.95, 0.97, and 0.95. In bracket 5% level of significance. From the given data, my null hypothesis is that the average weight in each and every box is 1 kg, and H1, the alternative hypothesis. Look, even the lesser is not accepted, neither the more than 1 kg is accepted. So that's why what I'm writing my null hypothesis as mu is not equal to 1. So the table that we will use here is two tail table. Okay. Then what is the value of n? So out of all the production, you have drawn a sample. The sample size is of 12. So the value of n is 12. Right? What was x bar? Remember, x bar was the mean of sample. The sample is of this 12 units. So what we are going to do, summation xi divided by total number of elements, which is 12. So that is going to be, you do this calculation. I will directly write down the answer here. So that is 0.9883. Then what we need? We need the value of s. How do we find out the value of s? S is equal s square. The formula was given for s square. So what I'm going to do? I'm going to do under root summation xi minus x bar square. What was in the division? N minus 1. Okay. So the answer is 0.001164. Okay, now we have all the values. Now t distribution, what is the degree of freedom? N minus 1. N is 12. So 12 minus 1, 11. What is the formula? The formula is x bar minus mu divided by s upon under root n. Let's put the values. X bar is 0.9883 minus mu is 1 into this root n in the numerator. So that is under root of sample size is 12. Under root 12 divided by s, which is 0.00164. So with this is minus 1.1881. So mod of t distribution, which is 1.1881. We'll look at the table value, and T with 11 degrees of freedom, level of significance 0.05. So with this we are going to look into the two-tailed thing. What is the two-tailed value here? So that is 2.201, which is larger. Calculated value smaller than table value. Accept or reject? We accept it's not. Okay. So the last test of hypothesis that we need to uh, look at is the F test. And the thing in the, you can see that in the first one, chi-square, what we were looking at was whether a certain probability distribution fits good to the given fits good to the given data or not. In the second one, the students t distribution, what we saw was, we saw whether the mean for the given data is I mean fits good to the complete population or not. And now what we are going to do is, we are going to compare two different datas, right? So there is first data, there is another data, and what we are going to see that whether the ratio for the two of them is right or not. Their variance is same. In short, the variance for the two data is same or not. That is what we are going to look at. So just give me a minute so that. So this formula is going to be used. Okay. So the object of the F test is to find out whether the two independent estimates of population variance differ significantly. Okay. So we have first data, we have the second data. So in both of them there is some variance for the first one, there is some variance for the second one, and we what we do is using this test I can check whether there is a huge difference in the variance of the two data. Let me just recall in your statistics part, what we saw was variance is nothing but the deviation of the data from its mean. Okay, say for an example, if you compare Rohit Sharma and Virat Kohli, say for an example, okay, what you will observe is the consistency for Virat Kohli is more than Rohit Sharma. Okay, so what makes me come to this conclusion is that if you look at each and every match and uh, the mean of the runs, I'll take the mean of say 10 matches. So the deviation from that mean value for Virat Kohli is lesser, whereas the mean, the deviation of the mean from the data from the runs for Rohit Sharma is larger. Okay, so in some matches he may get out at say 0 runs, whereas in some matches he may score a century, whereas Virat Kohli is almost consistent. Okay, so that is what we mean by the variance. So here, what we are going to check is, say I have first data, I have second data, and there is a variance for the first data, there is a variance for the second data, and whether there is a deviation. There is significant difference between the variance. That is what we are going to check using the F test. So the test of significance, this formula is important. Let's just see what is F. So F is nothing but S1 square upon S2 square, where S1, this is the same formula that we used in the t test. So summation x1 minus x1 bar square upon n1 minus 1. What is n1? The sample size for the first data. X1 bar is the mean for the first data. Similarly, S2. So x2 minus x2 bar, the mean for the second data, upon n2 minus 1, which is the sample size for the second sample. So it should be noted that S1 square is always larger estimate of variance. So S1 square is greater than S2 square. Note that the numerator is larger. There is nothing particular about S1 and S2. Those are just the notations, but whichever is larger needs to be in the numerator. That is the conclusion. Fine. So F is equal to larger estimate of variance upon smaller estimate of variance. So first of all, we will find S1, we'll find out S2, then we'll see which one is larger, then I will keep it in the numerator. So new 1 is N1 minus 1, new 2 is N2 minus 1. So degrees of freedom for sample having larger variance, and new 1, degrees of freedom for the sample having smaller variance. The calculated value of F is compared with the table value for new 1 and new 2 at 5% or 1%, whichever is given in the question. Okay. So what we are going to do is we'll find out the value of F. Then I will compare it with the table value, just like the previous two cases. So if the calculated value of F is greater than the table value, then the F ratio is considered significant. and the null hypothesis is rejected. Let's read the statement once again. Calculated value is greater than table value. This is the same thing just like we've seen in the previous cases. If the calculated value is larger, then we reject. If the calculated value is less than table, then we accept the hypothesis. Just same to the previous one. Okay. Now, since F test is based on ratio of two variances, it is known as variance ratio test. Thing new. Again, just the kind of remarks. So we assume that the two of the data which are given, those are normally distributed. Even in the student's t-test, it was there. In the student's t-test, I said that if the population follows normal distribution, then and then only we can take out a sample, apply t-test and check the hypothesis. Fine. Let's look at an example. So two samples are given. What are the two samples? The two random samples were drawn from two normal populations and their values are. So you can see that there is a sample A and sample B. From where I have took this sample? From a population which is normally distributed. Okay. So what is the value of n for the A? 1, 2, 3, 4, 5, 6, 7, 8, 9. And for B it is 11. Test whether the two populations have the same variance at 5% level of significance. Also in the question it is given the value of f is 3.36 at 5% level of significance for nu1 as 10, nu2 as 10. Let's recall what was nu1 and nu2. Nu1 was the degree of freedom for the larger sample, and nu2 degree of freedom for the smaller sample. How do we get the value of f? F is nothing but s1 square upon s2 square. Okay, so we have a. How do we get x bar? Sum up this all the values of a divided by the number of samples. So 9, 720 divided by 9, 80 is the mean. So x1 minus x1 bar, we got the values, add it up, turns out to be 0. Similarly x2, add it up, summation is 0. Okay. So x1 square we have found out, x2 square we have found out. Why did we find out this? Let's go for the value for formula for s1 square. S1 square is summation x minus x1 bar square. So x1 bar is 0 for that example. X2 bar is also 0. So simply we have summation x1 square upon n1 minus 1. And so s1 square is summation x1 square upon n1 minus 1. S2 is summation x2 square upon n2 minus 1. So we have got this values. So f is equal to s1 square upon s2 square. So that is 0.707. The new one is 10, new 2 is 8. Okay, this is the calculated value. The calculated value of f is less than the table value. The hypothesis is accepted. Okay, just like the previous one, nothing new. Similarly, the next example, in a sample of 8 observations, the sum of squared deviation of items from the mean was 84.4. So sum of squared deviation of items from the mean, which value is given? X1 minus x bar square is given. In the another sample of 10, The value was found to be 102.6. Okay, so x2 minus x2 bar square is given. The sample size for both of them is given. So n1 is 8. These are the values given. So f is s1 square upon s2 square. So s1 square we have got 12.06. s2 square is 11.04. The value of f is 1.06. New one, which is n1 minus 1. So the sample size is 8. So 8 minus 1, 7. New 2 is 9. The level of significance 5%. The value of f is 3.29. So the calculated value is smaller than the tabular value. Hypothesis should be, the variance that is not significant. Okay, difference in the variance of two sample is not significant. Okay, again we have two samples given. The sample size for the first one is 3, 3, 6 and 8, and for the second sample it is 10. So we have s1 square, s2 square. I think this is the same example again. No, it's not same. Yeah, so x1 minus x1 bar, it turns out to be 0. So we have done x1 square. Similarly, x2 square as summation x2 is 0. So x1 bar is this, x2 bar is this. Then we find out the value of s1 square is 90.857. s2 square is 133.33. s1 square upon s2 square turns out to be 0.681. So we look at the tabular value in this case. The tabular value with 0.05 level of significance. New 1 is 9, new 2 is 7, which is 3.68. So calculated value is smaller. Hence the two population have the same variance, which means that there is no significant difference in the variance. That's what we mean to say here. In this particular sample F test, if you are accepting the hypothesis, it means that the variance has no significant difference, right? The variance is almost similar for both the samples. Fine. And the next one, I won't go into the details of this last example. I'll give it in the tutorial so that you can solve it. Fine. So that's all about probability and statistics.